The Earth is the only home we have. Researchers at higher education institutions around the globe are working on solving some of our most complex problems, but it's impossible to do this kind of science without significant support. The study of biology and oceanography, climatology and astrophysics, geology and bioinformatics all increasingly rely on one thing to enable their potentially life-saving work.
My name is Eva Diomen. I'm a research professor in the computer science department at the University of Southern California. I'm also a research director at the USC Information Sciences Institute. I'm a computer scientist by training, and I work in distributed systems primarily, working on issues of management of scientific workflows, resource management, and others.
The power of distributed computing comes from our ability to take one machine, connect it to other computers, and distribute the processing load across those many other machines. There are practical limits, heat, power, space, to the number of machines that can be connected in distributed systems. But those limits are mitigated by the ability to connect to other distributed systems, which are themselves distributed geographically, usually in HPCs, high-performance computing centers. To enable these connections, dedicated, high-speed internet networks are required to link the systems into what are referred to as grids. To supplement the grids, high-capacity storage is almost always included in the HPCs. To this foundation of computing, networking, and storage, we add instruments like telescopes or remote sensors, along with methods for transmitting their data. Then we add software, middleware, and user interfaces. And finally, to round out the cyber infrastructure ecosystem, it is the scientists who are conducting the research. Let's take a look at what the inside of a data center supporting high-performance computing looks like.
This is what's called high-performance computing. So each of these racks are full with HPC platforms, and on the other side is the storage that supports those platforms. So this is all utilised for medical research, and it's a consortium of UCL, the Francis Crick, and the Sanger Institute. So they've come together as a single entity, if you like, through funding to provide this service and then take forward medical research within the building. Storage is 10 petabytes of data, and the IT load that is supported by is some 190 kilowatts of power. This is the single largest installation of its type outside CERN.
To get a sense of the scale of the amount of data, 1 petabyte is equal to 1,024 terabytes. 1 terabyte is equal to 1,024 gigabytes. That means that 1 petabyte is equal to 1 times 10 to the 6th gigabytes. What would it look like if you used iPhones to store 10 petabytes of data? Assuming an iPhone 13s with 256 gigabytes of storage at a unit cost of around $949, you would need 39,063 of them to store 10 petabytes of data, and it would cost approximately $37.1 million. High-capacity storage is probably a better bet.
Cyber infrastructure is a lot of things, and you need to have a lot of knowledge in a number of different areas to reutilize and develop cyber infrastructure.
Another important part of cyber infrastructure is that it is interoperable and collaborative. You don't just build one thing and call that cyber infrastructure. If it lives on its own in a silo, then it's not part of the cyber infrastructure system, right? And so it incorporates many technologies. That might be high-performance computing, it might be storage, it might be networking, it might be services, but they all have to work together and at every stage of the research life cycle to all work end-to-end to support the research that we do.
Yeah, so the promise of cyber infrastructure is to provide scientists, researchers, engineers with computational capabilities, like in a big sense. So it could be with all the cyber infrastructure basically that comes together to put it in the hands of the scientists so that they can do their work as efficiently as possible, so that they can have the breakthroughs that we expect from astronomy, bioinformatics, ecology, you name it. Basically, cyber infrastructure is there to serve the scientific and research community, and we want that to be as easy to use as possible.
The Open Oceans Initiative is an NSF-funded project enabling access to significant amounts of data through cyber infrastructure.
So OOI is offering access to huge amounts of data for a broad range of scientists to study processes in the deep ocean in real time. In my research, I use video data from the HD camera system at Axial Seamount to study how bacterial material in the water column changes, and those reflect changes in the underlying hydrological system. So having continuous access to your instruments and to data from the seafloor is really the future of ocean science.
The OOI has played a key role in my career as an oceanographer. I designed my postdoc research around the data being gathered at the Erminger Sea Array, and then received NSF funding to modify the design and sampling plan of a glider there. So now that data is being sent to me in real time through the cyber infrastructure, providing a powerful opportunity to be able to look at carbon cycling in the high latitudes year-round.
The fact that there is no curriculum per se in education, there's no cyber infrastructure courses. So everything is done by the projects that work in the area of the cyber infrastructure.
Cyber infrastructure is inherently interdisciplinary. Higher education has, so far, resisted interdisciplinarity, broadly speaking, continuing on in the departmental and college silos that have historically been in place. In a recent editorial in Nature, authors argued that doctoral programs are not effectively training researchers to meet society's expectations and needs, and arguing that the academy needs to rethink its approach. Interdisciplinary programs like cyber infrastructure may be a good start. So, is it true that there aren't any cyber infrastructure classes or programs? Let's start by looking at the top engineering institutions in the United States. Surely, MIT will have a robust cyber infrastructure program. Results not found. Same result at Carnegie Mellon, searching their graduate catalog. And at UC Berkeley, results not found. Nothing at Georgia Tech either. Finally, a result. The University of Illinois at Champaign-Urbana offers a Cyber GIS and Geospatial Data Science master's degree, and they host the Cyber Infrastructure and Geospatial Information Lab. The Cyber GIS and Geospatial Data Science master's degree references many aspects of cyber infrastructure: high performance and data intensive computing, data analysis, management, processing, and visualization. It is true that there are not many cyber infrastructure programs in place, but perhaps with a focus on interdisciplinarity, that will change.
So there are a number of initiatives that aim to make cyber infrastructure as easy to use as possible. The MSCC, which is a minority serving computing consortium that aims to provide training and cyber infrastructure literacy and capabilities to the campuses around the country that serve minorities. So that's quite an ambitious effort to basically democratize access to cyber infrastructure. And altogether, this notion of democratization has become very important in NSF and in general in the US, to make sure that researchers and students from a variety of institutions can leverage these capabilities that are being funded by NSF and others.